Okay, good morning and good new semester to ELEG 422-622. Today's the first lecture, which I'm recording for September 1, 2020. And today we're going to jump right into it. First I'm going to go over the syllabus that is posted on the Canvas website. Now, we can discuss this during the group me session tomorrow, but there's multiple communication channels going on here, including this video, and I am going to utilize Canvas and PO Box and email and various things as we go through the semester, and I realize that that's a little bit perhaps overdone. But I know some people like Canvas, and I like email because I know I'm putting it in front of you. So there may be a little bit of duplication of communication going on in the semester. But in any event, you should recognize the syllabus that's put up on Canvas, which is the document I'm holding in my hand. And the syllabus for this course requires a little bit of clarification. The course is a little bit unusual in terms of normal engineering courses, and it's unusual because there's sort of two ways to approach semiconductor materials processing, and we have to kind of do it both ways. The first way is semiconductor materials processing is a set of process technologies or process steps that exist in the clean room that allow you to fabricate a semiconductor device. And in this section D here, I list them: thin film deposition, which is basically the method by which you deposit films of material on a semiconductor wafer, and we'll go through why you deposit thin films and how you do it. Epitaxy, which is a form of thin film deposition. It's just that it's thin film deposition of a crystalline material. And then we get into what's called lithography, which is the development of patterns on the surface, which is sort of akin to photography. There's E-beam lithography, which is used primarily for making the mask plates for optical lithography, which is the next one. That's supposed to be wet and plasma etching of thin films in semiconductors. Basically, that's how you define, I guess you would say, topographical or mechanical features in the wafer. Wafer cleaning, that seems out of step there, and that sort of illustrates one of the issues with this textbook. It's a really nice textbook because it has a lot of nice things in it, and it especially is sort of oriented toward research grade semiconductor processing. Which is an aside. I mean, a lot of you are in here because you're in research groups where you're going to have to go into the clean room and do some processing. So you sort of need to know, in a research lab how you process. But in any event, yeah, wafer cleaning is a little bit out of order there. But and I'll skip 7 and 8. Well, I'll skip to the rest of them because Section D goes through a set of capabilities in the clean room, and it's I like to make comparisons between semiconductor processing and working in your kitchen at home, preparing some, like baking a cake or something like that, and so I mean, if you were to have a course in how to operate in the kitchen, which I'm sure there are such courses, you might go through, okay, you know, how does an oven work, you know, and how do you use it, and how does a microwave oven work, you know, and how do you use that, and how does your refrigerator work, you know, and what temperature are things kept at, and you know, even like wafer, you know, cleaning. I mean, how does a dishwasher work, you know? So, you know, analogously here, I mean, you can think about going through, you know, a set of sort of instruction manuals for, you know, how to do the various, how to operate the various pieces of equipment in the clean room, and go from there. Um, and along those lines, you will notice on Canvas at least, is that I did manage to get a set of 5 videos of one of our graduate students, Nam, operating the equipment, and those are up, and they should be in the media section of the Canvas pages. So please let me know if you're able to access those videos. They're very nice. They're an extremely nice addition to the course, and you know, those will aid in understanding how you do operate these various pieces of equipment. Now, you know, getting back to the kitchen analogy, so you know, I mean, if you were to learn how to prepare food, you know, you might take a course where you're basically, there's chapter 1 is how does the oven work, chapter 2, how does a mixer work, you know, I mean, etc. And you know, that might be helpful, but it's sort of more natural to learn how to prepare food by going through certain recipes. So for example, I mean, a recipe could be for how to bake a cake. And when you bake a cake, you use those various pieces of equipment, you know, that you would have learned how to use in that other way of going through things. You know, it's just that it's not taught that way because, okay, first you prepare the pan and you turn the oven on preheat, and then you do this and do that. And so the point I'm trying to get at here is that what you're meant to learn in this course is how to make a semiconductor device. And what that means is that, okay, we could have started by going through, okay, say I want to fabricate a laser, a semiconductor laser. What do I do? And we could go through all the steps of doing that. And the problem would be that as we're going through the steps of, for example, you know, if the next step is operating a proton implanter, well, I mean, it won't exactly be understandable to you going through that recipe if you don't know what a proton implanter is. So, you know, it's kind of a catch-22 thing where, okay, learning how each piece of equipment in the clean room works and how to operate them is somewhat devoid of a good feeling of understanding, because unless you're doing something with them, you don't kind of get what you're doing it for. But at the same time, if we jump straight to recipes and how to make things, well, then, you know, as you're going through the steps, you're like, well, I don't know what a proton implanter is, so I have no idea how to do that step anyway. So the course kind of has to be taught twice in a sense, and that's where you know, we get to the syllabus on the second page, which is, you know, a set of letters A, B, C through M, and so A through L are these pieces of equipment and or process steps that you perform in the clean room, you know, as we go through them, sort of in the order in the textbook, or well, basically in the order of a textbook, and you learn all those steps. And then M is, okay, we're gonna perform some recipes now, and so you know, we're gonna fabricate a device. And I sort of left that open because we'll see how far we get in the course, basically, in terms of, you know, I mean, there might be M1 and M2 and M3 in terms of different devices that we go through the fabrication steps of. And the point being that in A through L, you've learned those pieces of equipment, and then in M, which there may be more than one M, we go through, you know, a particular device, like a particular recipe, how to make pancakes, and you know, and then you know as we go through the steps what we mean when we say do this step. So hopefully you got the idea there of what we're going to try and accomplish this semester. Now, most of that stuff, in the context of this course, and in reality in the context of actually doing things in the clean room, is essentially knowledge-based, okay? You know, as we do optical lithography, right? I'll go through how you do optical lithography. You take a semiconductor wafer, you spin photoresist on it. You pre-bake that photoresist to drive out any solvents. You perform the exposure and a development, and you do all these things that result in a developed stencil on a wafer of photoresist. And you know, that's like, okay, a set of knowledge. It's like, how do you do that? There's very few equations or math involved with optical lithography. I mean, there can be, but you know, it's kind of just understanding how it works and being able to go through it. So most of the course, when it comes to testing you, which I'll get into, you know, how I'm going to do that in a second here, is you know, kind of knowledge-based. It's like, okay, explain to me, you know, why you would spin photoresist at one speed versus another, or why you would use this photoresist versus another one. And so what you'll mainly be tested on are those knowledge aspects. Now, there are two steps here that I have to single out, H and I. So let me start writing here. Syllabus. So let me put it this way, A through F and J through L are, you know, knowledge-based. Knowledge questions. So to speak. Now, there are two things here, H, oxidation, and I, dopant, diffusion. And for those subjects, they're sort of actual math. And you know, the actual math is like for oxidation. Okay, if I want to oxidize and make a layer of silicon dioxide 1 micron deep, how long do I oxidize? You know, in this. And the point is, you know, there's a theoretical knowledge base there that you need to understand, and I guess it's kind of like, I mean, well, I'm trying to think of an analogy in the kitchen. I mean, in the kitchen, if you've ever like baked a cake or made a recipe or something like that, you know that there's very little calculus involved. I mean, you go by a recipe and you may, you know, alter it by taking proportions and things like that. But these two steps in particular have to have a theoretical understanding to them. And I'm not coming up with something in the kitchen, but I mean, it's sort of akin to, okay, if I were baking a cake, but as part of that step were to expose the cake to some environment so that to a certain depth in the cake it became something different, I don't know what, you would have to understand the theory behind that in order to do it. So, the course is a lot of like, okay, questions, like, why do you bake at 200 degrees in this step? Okay, and you're supposed to be able to come up with the answer. And then these two things where it's like, oh, okay, here, this is like physics basically. So it's this little bit of a mixture here, and we'll go through it, and my goal is to make sure that you know how to do both of these. I suppose that's a good thing to talk about testing and grading. Now, normally there would be midterms and a final and all that good stuff. This course, I mean, really lends itself more to, since a lot of it is this, quizzes anyway. And so we will be having quizzes during class. Quizzes, not sure to spell quizzes. During class. And homework. So, because of the situation we're in, homework will count for a lot more than it normally would have in the past. And the reason is because, I mean, really, it just seems a little bit impractical to me to ask good engineering exams where, I mean, it can't be assumed that there's access somehow to material. And so why not just make it homework? So there will be homework in the course, and the homework will be more important. So if you're the kind of student that doesn't like to do homework, and I've noticed there are those kinds of students, I don't know why. To me, homework is absolutely the first thing that you should ever do in class, because you can make sure that you get a good grade in homework. I mean, because you can, the more effort you put into homework, the more likelihood is you're going to get a full score on it. So do the homework. Even if you're a student that doesn't like doing homework, and I know that there are those of you out there that are used to, sort of not really focusing on homework, knowing that you can pass tests. Because of the situation we're in, where this is online, homework is going to be very important here. Okay, and we can talk about that more back and forth during the chat sessions when you're able to reply. So that's the syllabus, and we'll walk through it again a little bit tomorrow afternoon or morning, 11 o'clock, when we have our little chat session. So I was going to jump right into it. Let me see what I'm up to here. 18. Okay. Maybe I won't complete this, but I was going to jump right into this handout that you should have gotten on the doping and conductivity of semiconductors. Now, the reason this is basically those of you that have taken my course ELEG 446646 or some other course in solid state physics will recognize all this and understand that we're going to do a little bit of semiconductor physics, and he does do a little bit of this in the textbook, but not really enough. And basically, what it comes down to is you have to be able to understand how to calculate the conductivity of a semiconductor from doping levels. The point being, you know, if now it turns out that if you go on to if you go online somewhere, for example, Virginia Semiconductor, and you buy a silicon wafer, it'll come quoted having a certain conductivity or resistivity, like 1 ohm centimeter or something like that. Now, I mean, you know, conversely, in that case, if, for example, you're going to fabricate a diode in that wafer through diffusion, you have to understand when it was quoted to have that conductivity or resistivity, what the doping is, okay? Because you need to know where, you know, you're going to design a device. You're going to take the silicon wafer that's p-doped, and you're going to implant n-doping, for example, or diffuse n-doping. And so, and if you want the junction at 1 micron, you know, you need to know what the doping level is in order to achieve that of the underlying wafer. So this goes backwards too. If you know the conductivity, you need to be able to calculate the doping levels. And so there's just a little bit of basic semiconductor physics that we go through. And those of, like I say, this will be a review for the people who have taken like 446, 646. Now, if you haven't taken semiconductor physics, and this is the first semiconductor course that you're taking, well, it's going to be a little bit more difficult because, I mean, first of all, I'm using this word doping like you know what I'm talking about. And I guess what I suggest there is that we just get started here. All right. Now, what we're going to do is we're going to get started, and we're going to imagine a semiconductor which consists of atoms, and free electrons. So these electrons are your conductors. They can move. Now, those of you in the know, and we'll you know, augment this picture with holes in a bit. The charge carriers can be positive and negative, but let's just go through this. So what I'm going to do is I'm going to walk through this sort of very quickly, because, okay, imagine this is inside a piece of semiconductor. So where we've zoomed in inside that semiconductor, and there's these mobile charges that can move. And let's say we put electrodes okay, so we have a voltage across the semiconductor. And so inside the semiconductor, there's an electric field E. Now, I am assuming when I say the word electric field, you know what I'm talking about. So you've had some modicum of physics here. And then the force, I mean, it's in the opposite direction, but the force on that electron is given by the charge of an electron times the electric field. F equals charge times field. And F equals ma. Now here I got to be careful to have a capital V for voltage and a lowercase v for velocity. All right, and so what happens is that when I apply that electric field, these charges are going to start to accelerate and their voltage is going to go up linearly. And so if you solve this equation, okay, dV dt is equal to E over m, right? Just putting that over there. And so v, the velocity, is equal to E over m t. And what we have is that as a function of time, the velocity is going up linearly. All right, now that's not what, I mean, that's what happens for a while, but obviously that's not what really happens. The velocity doesn't continue to increase without bound. What happens is that these carriers, these charge carriers, as they move, at some point they're going to do what's called scattering, which is basically bounce off of something. And when they do that, their velocity is going to suddenly drop to zero, essentially. And it's like they ran into something and then just stopped, okay? And then they're going to start accelerating again, and so on. Now, there's something called the average velocity, which is also called the drift velocity. Okay, I'm going to try and be neat. All right, now what is that? Well, if this time is tau, that's the scattering time, that drift velocity or average velocity is E tau over m. Now, you may be wondering why it's not half that, right? Because that would be the average velocity. This, right, if you think about it, this is E tau over m. So you might think there's supposed to be a 2 there. Well, there isn't, and the reason why is because this is a three-dimensional solid, and so when you take into account the statistical motion of the particles and calculate an average velocity in one direction, the direction in electric field, that 2 goes away. And, you know, I mean, I don't see no point or any point going through a more difficult analysis to come up with an answer to get rid of a 2. And so, you know, you just have to remember that in this F equals ma, you know, F is E times electric field. All right, the average velocity is actually the peak velocity obtained in the one-dimensional situation. And so, you know, that's how I want you to remember it. And so you can put a box around this. Now, so what that tells you is that for a given electric field, or a given voltage, because electric field is voltage divided by the length, L, or electric field is voltage divided, yeah. that there's a particular drift velocity, and you can calculate it if you were to know the scattering time. Now, the mass of the electron, we're gonna go through that, is not the mass of a free electron, but we'll walk through that part. And this drift velocity is a number. You can calculate what it is. As I said, if you know tau and m. Now, the one thing I want you to realize, which you don't, for the purpose of the course, you don't need to think beyond this point. Tau is independent of electric field, and that's a little wrinkle in the analysis that if you haven't worried about that, you don't need to. If you're looking at this and thinking about it, you realize that since this velocity goes up with electric field, you may think that tau is affected by that because things go faster. All right, and it doesn't. Tau is not a function of electric field. And the reason why is because there's another velocity. Okay, if there were no electric field present, these particles would still be in movement. For the same reason that the air in this room, the molecules have velocity, okay, even though there's no wind, of course, because of temperature, okay, they have thermal energy. And it turns out that if you calculate that thermal velocity, the thermal velocity is typically much larger than the drift velocity. So it means that the time between scattering events is governed by temperature. And the electric field, which governs this, has very little impact. And what the consequence of that is that we have Ohm law, which is that current goes up linearly with voltage. All right, so after that little wrinkle, we need to calculate J, the current density, which is the current per unit area, which, remember what current is. Current is charge per unit time per unit area. Now here, this is what's the flux of charge. And the word flux here refers to the movement of something per unit time per unit area. So the flux of charge is the charge per unit time per unit area. Now we could elaborate more on flux and possibly could. I think that if a student wants to talk to me offline about that, I can go into that more detail. But the flux of anything, the flux of a thing, is equal to the thing's per unit volume times the velocity. okay? And if you look at this, right, so the flux of a thing is the movement of the things per unit time per unit area. All right, well, there's things per unit volume. Velocity is distance over time, and so the units work out. All right, and again, you know, we could spend the rest of the half of the lecture, you know, on proving that to you. But let's just go on here. So J then is equal to the things per unit, okay, it's equal to the charge per unit volume. All right, what is the charge per unit volume? Well, it's E times N, where this is the charge of an electron, and this is the electrons per unit volume. Okay? Okay, that's the charge per unit, you know, because when I multiply times the charge on an electron, that gives me the charge per unit volume. And so I multiply that times the drift velocity. And that's J. So J is defined from understanding how to calculate the flux of something. All right. Okay, and then we just, you know, sort of fill in the blank. So that's E. I'll write it a little bit nicer. E times N times the drift. E tau over M. So it's equal to N E squared tau over M times the electric field. And we define that as the conductivity sigma. You know, that's basically it. And I'm going to put a definition there because that's basically defining sigma. Now there's another definition here, which is mobility. Mobility is defined as the ratio of the drift velocity to the electric field. So we can also write J as E N, and then plug in for V drift, U E. And so we see that sigma is equal to two things. It's equal to NE squared tau over M, and it's also equal to NE mu. And so from that we get that mu is equal to tau over E tau over M. So, you know, we've introduced this term mobility, and that's because for a semiconductor, mobility contains the ratio of tau over M, and so you don't need to know those things. Which, you know, to a certain extent, I just swept under the rug the whole thing about effective mass and all that stuff, and so we can reserve that for semiconductor physics, for 446 and 646. So what I want you to remember from this is that J, or that sigma, sorry, sigma is equal to NE mu. Now, what I'm going to do is I'm going to write down two things here. Now here, what I've done is I've introduced holes. All right, now if you haven't taken semiconductor physics, all I want you to realize or understand is that a semiconductor, okay, it's natural to think about negative charge carriers, electrons, but there can also be positive charge carriers, and that's something you don't understand until you do semiconductor physics. I don't want to repeat several lectures of semiconductor physics. So this is the electrons per unit volume, and this is the holes per unit volume. And you have to, because the electrons and the holes have different mobilities, you have to plug them in. They're not the same. Okay. I think we're going to stop there for today because number one, I don't want to get too much into technical material in the first lecture, and also I don't want to overload YouTube, which took 3 hours to load the other classes this morning, and so this is the milestone for today's lecture, the conductivity. Now you have to understand, you know, what conductivity means, okay, so you know how to use it. But basically, it's given by this formula, the charge on an electron times NUE plus PUH, where these are the mobilities for electrons and holes. And we'll just stop there for today.